Welcome, my friends and colleagues, to introduce the aspect of thermal design for the boreholes in a geothermal heat pump. In this episode, I will introduce the characteristic of a borehole heat exchanger and its installation in the ground, accompanied by its main components to construct a heat exchanger that is called borehole type, which is a vertical heat exchanger. In this part, I will cover the construction of the heat pump itself and the borehole and how can we estimate the depth of the U-tube in the ground, which is related to the properties of the geological aspect for the ground and the thermal properties of the grout or filling that is surrounding the U-tube in the ground. Thank you for continuous support and let us keep on this series of videos in this field, which is the renewable energy source called geothermal energy. The objectives of the present episode cover the geothermal heat pump components. The main components, of course, I will pass through. And then we have the direct contact geothermal heat pump, which refers to the contact between the heat exchanger, which handles the circulated fluid in the heat pump and the ground. Then we will go through the estimation of the depth for this heat exchanger, which is in effect, we are calculating the surface area of the heat exchanger to achieve a certain heat or cool load. And finally, we will approach, as usual, the closure for the present episode. In this system, we have the heating mode where Earth works as an energy source to the fluid which passes through the borehole in the blue direction, which extracts energy from the ground and then return back to a heat exchanger, which is a part of the heating pump. Then this fluid will give energy to another circulated fluid, which we have explained in the previous slide, and then that will provide energy to space. In that way, we have extracted energy from Earth and transferred to the, for example, domestic use in this example, then heat can be transferred from ground to the utility. In this case, we have the utility as heating for um, house or maybe in a restaurant or other applications. So this is the heating mode, how the heating mode operates. Here we have a vertical heat exchanger, which is called borehole heat exchanger, that is installed vertically uh, inside Earth. It is composed of uh, YouTube, and the YouTube is installed inside a bore, surrounded by grout material, and this grout material should be conductive material to facilitate heat transfer and conduction between the soil, the external part as shown in this figure, and the tube itself. So in that sense, we are uh, extracting energy from the soil, which represents the earth structure, conducted to the grout, through the grout material, to the tube surface, all of that in conduction, and then by convection to the fluid which is passed inside that YouTube, and it could be water, shown in the right hand side photo, water inlet and water outlet, water inlet representing the blue one, and the outlet is the green one. So hot fluid or hot water, we will get it from that bore hole, and can be used for heating purposes. Almost similar system can be used for cooling system as well. The DX geothermal evaporator in a heat pump. And here we have the evaporator, which represents the ground part of the heat pump. So the other parts represent the condenser, compressor, and expansion valve. This is for the construction of the heat pump. But for the evaporator, we will have the underground heat exchanger or the borehole heat exchanger. So the liquid, after leaving the other parts of the heat pump, enters the heat exchanger through the blue line, blue part of the U-tube in the ground, and it extracts energy from the ground, then it is heated up and then evaporated. So it will leave the heat exchanger in the red line part of this illustration, and return back to the uh, unit of the heat pump as a vapor, which passes through the compressor and then condenser, and after that through the expansion valve, which can compose a closed circuit for the heat pump itself. So what we have here is the fluid which is circulated in the heat pump is the same as the fluid which is circulated in the ground heat exchanger or the borehole heat exchanger. That's why it is called DX geothermal, to refer to the process where a direct contact for heat transfer between the ground and the fluid circulated in the heat pump without the need for an intermediate fluid to transfer energy. Here we have the condenser, which represents the fourth main part of the heat pump itself. So we have the underground heat exchanger, the borehole, represents the condenser, and the other parts which compose of uh, evaporator, compressor, and expansion valve represented by the other side, which is out of the ground. Then what we have, the ground part represents a condenser. Here we have the refrigerant vapor, which is circulated in the heat pump, passes through the inlet part of the heat exchanger through the red line, and then it reject energy to the ground, of course, through the filling or the grout to the ground, and then returns as a liquid refrigerant to complete the closed circuit of the heat pump. Again, this is a DX geothermal condenser because we didn't need an intermediate fluid to transfer energy to the ground, because the main principal part which represents the fluid that is circulated in the heat pump is the liquid which passes through the heat exchanger. We have the borehole depth estimation, which represents the main or the major part of this episode. Let us consider that we have a borehole with a single U-tube as shown in the photo to the left-hand side, and this uh, two sides of the U-tube are replaced by an equivalent diameter, which is called an equivalent diameter technique. Of course, this technique has been used for a long time by many investigators, but in the present model, this is the first time to be introduced. So, to derive this part, and we mean the equivalent diameter, usually it depends on assuming the same grout or filling material that fills the borehole is the same volume in both cases. Therefore, pi over 4d sub b square minus 2d naught square by times L, which represents the volume of the grout in the original geometry, equal to pi over 4 dB square minus dE square times L. And this is will produce that D equivalent equal square root of 2 times D naught. Of course, this equation has been even used by many models to represent the equivalent diameter in order to predict the depth of the heat exchanger. In the present model, we are assuming that even the surface area has an essential effect, that is the surface area or the contact surface area between the two geometries with the grout is an important factor. Therefore, if we assume that 2 pi d naught L equal to pi d equivalent L, that means we have the same surface area for both geometries. That will end with D equivalent equal to 2D naught. So in that equivalent diameter, then we will get the same surface area. So if we take the average value, that to include both effects in the final model, to include both effects, constant grout volume and constant surface area. If we take the mean value, then we will end with the equivalent equal square root of 3 times d naught. This is the final result of this model, which has been published by this reference, and I will list a group of references which describe the geothermal energy and depth of the borehole. And our reference here will be the first in the list of references. Let's examine the model which has been already established in this seminar. Let us consider a ground heat exchanger, which represents a condenser and a heat pump, with following conditions: that we have Freon 410A is circulated in the heat pump with a condensation heat transfer coefficient of 3000 watt per meter square degree centigrade, and it will be used as a typical reference value in the analysis. And we will use a copper U-tube where both legs have the same diameter as shown with in the table for the respective dimensions of these tubes. Three different geometries with the ratio of diameter to thickness, outside diameter. SP represents the distance between the centers of the legs of the U-tube. D sub B represents the borehole diameter, and the other dimensions represents the ratios. Then we have WF equal tube wall factor, defined as D naught divided by T, and we have T equal to tube wall thickness. The objective is to predict the depth of this heat exchanger. After using the characteristics of the heat exchanger, the U-tube, the single U-tube, in different correlations which are available in the open literature, we have found that the grout specific thermal resistance varies with the thickness, with the thermal conductivity of the grout, and all these models have predicted that this resistance is declining with an increasing of the thermal conductivity of the grout, and all of these correlations have shown the same trend for the grout specific thermal resistance. And we may find that these values are different depending on the WF value. The first figure on the left hand side for WF equal 14.29, and on the right hand side is represented for WF equal 17.86. So again, the same trend of the variation of the resistance, and we can conclude that Kg, which represents the grout thermal conductivity, has its impact and high impact on the performance on the of the borehole, and at the same time we may expect that the lower heated thermal resistance will be accompanied to the higher thermal conductivity, which is reflected, of course, on the depth of the borehole and the cost, of course, for the final design of the borehole heat exchanger. The total thermal resistance of the borehole is the key to calculate and predict the depth of the borehole itself. We have already shown that the thermal resistance, and here we have to mention that R sub B is the specific, and it means that the thermal resistance per unit length equal to filling resistance plus Rp. Rp refers to the total thermal resistance of the fluid passes through the tube plus, of course, that will be a convection part, and plus the conduction part through the tube wall itself. And we have the total thermal resistance equal to R sub B, the borehole thermal resistance, plus R ground, which represents the soil thermal resistance. Of course, that will be a specific as well. It means that the resistance per unit length. And if we substitute the values of R sub F, R sub P, then add to them the ground part, hence we will get the total thermal resistance. It has been found from some research that after 1 year of operation for the borehole heat exchanger, then it will approach, the ground will approach steady state conditions, and the thermal resistance or the specific thermal resistance of the soil or the ground will be equal to 0.053 meter Kelvin per watt when the thermal conductivity of the soil was 2.42 watt per meter Kelvin. To get the wattage per meter of the borehole heat exchanger, Q equal to delta T mean divided by R total. And R total has been found from the summation of all the thermal resistances. Here we have to mention that Q depends on delta T mean. And delta T mean refers to the temperature difference between the soil and the fluid that flows inside the heat exchanger. And to get the depth, then we will evaluate the condenser load and divide that by the specific wattage, which is W divided by meter, and Q dot condensation equal to M dot times H sub Fg, which represents the latent heat of evaporation, and here is the same for the condensation of the fluid that flows inside the tube. Here we have the total thermal resistance, the specific value calculated for the wall factor of 14.29 and compared with different references, and it's clear that the present work occupies the middle zone between the highest and lowest value predicted by other investigators. And it seems that the trend of the uh, thermal resistance uh, showed an reduction with the increase of the grout material. And we have calculated that for the other design or geometry, WF equals 17.86. Again, we have the same trend, and it seems that the difference between the highest and lowest value, of course, these values will limit the depth of the heat exchanger, and in that sense we have to be careful when we select the correlation to predict the depth of the heat exchanger itself. And again, it seems that the thermal resistance reduced as the thermal conductivity of the grout material was increased. My friends and colleagues, we have arrived to the final part of this video, which is related to the closure. We passed through the geothermal heat pump components, the underground part, which represents the borehole, and the other parts, which are on-ground parts, which includes compressor, expansion valve, and either the evaporator or the condenser for the direct geothermal borehole, where we have the fluid passes through the tube, the U-tube, and is the same fluid which is circulated in the heat pump itself. And that's what we call the direct contact geothermal heat pump. And I used one of my published correlations to predict the depth of the single U-tube, and it was compared with other published correlations for specific conditions of the heat load and the physical dimensions of the borehole. There are some valuable references you may find in the link in the description box for some references which are either used in this episode or in you may increase your knowledge about geothermal energy with the others. And usually I put the reference which has been discussed in this episode as the first reference in the list. If you feel that the information and the thermal design is useful to you and others, please subscribe to the channel and share it with your friends, and we hope can achieve the main goals of our for the creation of our channel. Bye bye.